Have you ever wondered how scientists really know something for sure? I mean, it's not magic, right? It's a method. It's a playbook. And today, we're going to walk through that exact playbook to see how researchers get from a simple question to a solid, confident answer. Let's get into it.
So here's the game plan. We're going to start with the absolute basics, what research even is and where it all begins. Then we'll look at the blueprint scientists create before a single experiment gets started. After that, we'll see how they connect the dots in their data, test their big ideas, and even handle more complex comparisons. And finally, we'll put all the pieces together to reveal the complete scientific playbook.
All right, first things first. What are we even talking about when we say research? Well, at its heart, it always starts with a question that needs a real, concrete answer.
I mean, think about it for a second. We are surrounded by claims every single day. This diet's going to help you lose weight. This app will make you more productive. But how do we separate what's real from what's just hype? That's the exact problem that scientific research is built to solve.
See, at its core, research isn't just randomly looking for stuff. The key words here are logical and systemic. It's a structured, organized, and totally deliberate investigation to find new and useful information. It's a process.
And get this, the origin of the word itself tells you so much. It comes from the French word recherche, which literally means to seek again. This shows you that science isn't about finding some magic answer on the very first try. No, it's all about careful, repeated investigation, about checking your work and seeking over and over until you can be confident in the truth.
Okay, so if research is a systemic search, then any good search needs a map, right? Well, in science, that map is what we call the research blueprint.
Before a scientist ever collects a single piece of data, they create a research design. And you should think of it exactly like an architect's blueprint for a house. It lays out everything in advance, all the methods, all the tools, all the techniques. This whole plan is what ensures the process runs smoothly and, more importantly, gives you a reliable result at the end.
So why go to all that trouble? Well, because the goal of most experiments is actually super simple, but incredibly powerful. It's to connect a cause to an effect. Does this pill cause the headache to disappear? Does this new teaching method cause test scores to go up? That's the fundamental question the blueprint is designed to answer.
Now, within those blueprints, you'll generally find two main flavors. The gold standard is the true experimental design, and its secret sauce is random assignment. When you can randomly put people into, say, a treatment group or a placebo group, you can be way more confident that any difference you see is actually because of the treatment. With a quasi-experimental design, the groups aren't random. Maybe you're just comparing two different classrooms that already exist. You might still see a connection, but you can't be nearly as sure about that cause and effect link. That's why randomness is such a massive deal in science.
All right, we've got our blueprint and we've collected all our data. Now for the really fun part, making sense of it all. It's time to start connecting the dots and actually looking for patterns.
You know, a lot of the time, the very first step is as simple as just plotting all the data points on a graph. We call this a scatter diagram. Before you do any complicated math, you just want to look at it. Is there a trend? Do the dots seem to be moving in a certain direction? Or is it just a random cloud of nothing? This first visual check gives you your very first clue.
Now, if it looks like there is a pattern, the next job is to make that pattern more concrete. That's where a tool called regression comes in. Regression analysis is basically the mathematical way of finding the one single line that best fits through that whole cloud of data points. And once you have that line, you can start making predictions. This is how we turn messy, raw data into a clear, predictive tool.
So, we see a pattern. We've even drawn a nice, neat line through it. But are we sure? Could that pattern just be a total fluke? A coincidence? Now we have to get really serious and put our idea to the test.
This whole formal process is called hypothesis testing. It's the official rule book for deciding if the effect you saw in your data is the real deal or if it's something that could have just happened by random chance. This is honestly one of the most critical steps in the entire scientific process.
Now, scientists start this in a way that might seem kind of backwards. They begin with what's called the null hypothesis, which basically assumes my theory is wrong. There is no effect here. It's kind of like innocent until proven guilty, but for data. The burden is now on the evidence to be so strong that it can overturn that initial assumption of no effect.
One of the most famous tools for this job is the student's t-test. It's a statistical workhorse for comparing the averages of two groups. And here's a fun fact for you. It was developed by a statistician named William Gossett while he was working at the Guinness Brewery in Dublin. He was trying to figure out the best yields of barley. He had to publish his work under a pseudonym, Student, and the name just stuck. Okay, I know the math here can get a little hairy, but let's just focus on the idea behind it. It's a pretty clear 5-step process. First, you state that no effect hypothesis. Then, you measure something called the standard deviation. That's just a number that tells you how spread out your data is. Next, you set your level of significance, which is basically you deciding how sure you need to be to believe the result. Then you calculate this thing called a t-value and compare it to that standard to make your final conclusion. We're focused on the why here, not the deep-down math.
A t-test is perfect for comparing two things, like a new drug versus a placebo. But what happens when our research questions get a little more complex?
Exactly. What if you're testing, say, 3 different potential vaccines, all against a control group? You can't just run a bunch of separate t-tests. Doing that actually increases your chances of getting a fluke result. You need a more powerful tool that's designed for this exact job.
And that tool is called ANOVA. It's specifically built to handle comparisons across multiple groups all at the same time. It lets you look at the whole big picture and see if there's a significant difference somewhere among your groups without upping the risk of a false alarm.
I know the name might sound a little intimidating, but it's actually really descriptive. ANOVA just stands for analysis of variance. And variance is really just another word for the amount of spread or variety in your data. So it works by comparing the amount of spread within each group to the amount of spread between the different groups. When you boil it down, it's all about analyzing that spread.
And there you have it. We've actually traveled all the way from a basic question to a pretty sophisticated statistical conclusion. So let's do a quick recap of the playbook we just uncovered.
See, it all kicks off with a clear question. From there, you build a solid blueprint, your research design. Once you get the data, you visualize it to look for patterns, maybe using a tool like regression. Then you have to rigorously test your idea using hypothesis testing, with things like the t-test for 2 groups or ANOVA if you have more. And only then can you finally draw a credible conclusion. That's a scientific playbook in a nutshell.
So the next time you see a headline about some new study, or you see a product that claims it gets amazing results, you'll have a whole new perspective. You know the playbook now. You can start asking the right questions. Was it a true experiment? How did they test their hypothesis? Knowing the process doesn't just give you answers, it gives you the power to question. So, what are you going to start questioning today?